Let's try again. I know. Still wrong. There we go. All right. So this talk is about quantum cryptography. And in fact, from a historical point of view, quantum cryptography was the first instance of quantum information processing, both theoretically and experimentally. And I will talk about both of these aspects. And I can't resist showing you this slide that was drawn by Christopher Fuchs, who was my postdoc at the time. Getting old slide. But the purpose of this slide is to illustrate that quantum cryptography required for its existence the collaboration of physics and computer science. And this represents Charlie Bennett at IBM. And that was me at the time when we met in 1979, and the field took off. And the person looking up on the dune over there represents Stephen Wiesner, 1970, who really laid down the first stone. And I will say a little bit about Wiesner's 1970 contribution, which from a historical point of view is extremely significant. Good. So I'm sure you've heard all kinds of things already today about quantum information. Is there a pointer? So I'm sure you've heard all about quantum information and all these strange properties. Thanks. All these strange properties of quantum information that make it so different from its everyday classical counterpart. So I'm not really going to go through these two slides, except perhaps to tell you that this is really dim. That what you've seen today probably had mostly to do with with the fact that quantum information can exist in superposition of classical state. That's really the essential aspect that makes quantum computing possible. But also, quantum information has other properties which are counterclassical, which sound somewhat negative. They sound like a nuisance. And indeed, for quantum computing, it is a nuisance. But for quantum cryptography, it's going to be really very, very useful. So we're going to build upon these properties of quantum information that cannot be cloned or copied or measured or disturbed by observation. Let me tell you what I mean by this. Using photon polarization as an example of quantum information. So if you think of photons, really, this is going to be a somewhat naive image, but it's good enough for my purpose. Think of a photon, the particle that carries light, as if if it travels from me to you, it is polarized in a plane perpendicular to the axis of propagation. And it's good enough, although naive, to think of it, this phenomenon, as if as it travels, it would oscillate up and down, and that would correspond to a vertical polarization, or it could oscillate left and right for horizontal polarization, or it could oscillate at any angle, like plus or minus 45 degrees or anything else. So the angle of polarization as the photon travels is a continuous variable. Any angle is possible as polarization. Now, when I say that quantum information, for instance, cannot be measured reliably, what it means is that it's impossible to build a device that would take as input a single photon of unknown polarization, measure it, and tell you with arbitrary accuracy what it is. So you cannot measure photon polarization with arbitrary precision. And then when I say that quantum information cannot be cloned or copied, it is to say that neither can you build an apparatus that would take a single photon, a gain of unknown polarization as input, and spit out 2 copies of it. So quantum information cannot be copied, cannot be measured, and moreover, if you try to measure it, you disturb it. And this is unavoidable. Any attempt at measuring quantum information not only yields partial information, but disturbs it in a way that's irreversible and forbids further measurements from giving you more information. Okay, again, this is an oversimplification, but it's enough to see the foundations of quantum cryptography. Now, of course, if you have not one photon, but a whole bunch of them, let's say produced by a laser, then it becomes possible. This impossibility only holds if you have a single quantum. And the more you have, the more precise and more accurate the measurement can be made when you have a lot of them. With only one, you can't do it. Now, some of you probably know about laser amplification, and laser amplification is something that seems to be doing just that, but not quite. And I don't want to get into the physics of why it's different. If laser amplification could do this, then you could make as many copies as you want. Once you have as many as you want, you could measure it, and this would be false. But laser amplification really does not copy quantum information the way most people think it does. In fact, it doesn't at all. Okay. Now, again, these properties of quantum information look pretty bad. This is nice. It allows us to do quantum parallelism and computation and all that. This has to do with entanglement. It's wonderful as well. This looks pretty bad. In fact, it's going to be very, very useful. Now, classical information is not something to be spit at. It's really useful as well. And in fact, the game that we play in quantum information processing can be summarized in this sentence, that we use both classical and quantum information. We use them together. So we don't oppose them. We use them together to achieve common goals. This is a very short list of what you can do with both types of information. And of course, today I'm going to tell you about quantum cryptography. And I'll talk about quantum teleportation on Thursday. And you'll hear about all the others. Maybe not this one, I don't know. But you'll hear about all the others during the week. But let me start with quantum banknotes because that's what this little Wiesner figure in 1970 here was all about. Quantum banknotes were invented by Stephen Wiesner. They look like this. So they are banknotes which are impossible to counterfeit, but impossible in principle. If you had one of these banknotes in your pocket, well, with current technology, it would probably need the whole space of this room to be kept for a millisecond. But let's think in the future, if you had one of those in your pocket, then you could be sure that nobody can make a copy of it. You cannot have counterfeit quantum money. And the essential idea, and I don't want to get into the detail because really I'm talking about quantum cryptography here, but I'm mentioning it because of its importance historically. But the point, the idea really is that you see this quantum banknote contains quantum information in there. And because quantum information cannot be, that's not what I wanted, because quantum information cannot be cloned or copied, as we saw before, then one cannot make a copy of it. Of course, you need a more precise statement and proof to say anything useful, but essentially that's the idea. Quantum information cannot be copied, and therefore a counterfeiter who would have one of those could not make copies of it. Good. Now, in 1970, just for the history of it, and for the record, in 1970 or late 60s perhaps, Stephen Wiesner invented this concept of quantum banknotes, wrote a paper that he submitted to IEEE Transactions on Information Theory, which is a computer science journal, but he wrote the paper in physics jargon in a way that's totally incomprehensible by a computer scientist, I'd say, and everyday computer scientist, at least of the time. So the paper was promptly rejected, put in a drawer, and forgotten about, except that Wiesner and Bennett were roommates at Columbia. And so Wisner told Bennett about his crazy idea, and nothing happened until I met Bennett in 1979 in Puerto Rico. Really, I was swimming in the ocean, just minding my own business. And then a complete stranger swims up to me and starts telling me about these quantum banknotes. It's kind of a shocking event, which changed our future. And by the next day, we had our first paper on the subject. Anyways, but this really, this was the burst, really, the idea that made quantum cryptography spark. So let me now tell you about quantum cryptography. Well, let me first tell you about classical cryptography. Here's the usual context. You have three parties named Alice, Bob, Alice, Bob, and the eavesdropper is called Eve normally, although this one doesn't look very female. And in this little picture here, Alice and Bob are just talking plain text. If you have some imagination, you'll see what he's saying. And that's why the eavesdropper is smiling, because he can overhear all that you're saying. And the purpose of cryptography, is the original purpose of cryptography, because there's a lot more, is to make allow Alice and Bob to communicate confidentially. So now they no longer, now they've enciphered and deciphered their messages, and the eavesdropper is no longer so happy. Put this one in the middle, perhaps. So what's happening here, essentially, this is purely classical cryptography, as it's been practiced for at least 4,000 years. Bob wants to say something to Alice, but if Alice and Bob have agreed upon a cryptographic system and upon a secret key, which they share initially, then Bob in this case can use, reverse again. Then Bob can use his secret key through some mathematical transformation to encipher the clear text, thus producing the ciphertext. The ciphertext is sent along to Alice, and an eavesdrop, and Alice, using the same key, can decipher it and figure out the clear text. Then he can keep talking. But the principle of cryptography is that an eavesdropper who intercepts the ciphertexts but does not know the key, even though he has complete knowledge of the all the cryptographic system being used, the only thing that the eavesdropper does not have is the secret key, will not be able to reconstruct the clear text. That's what we hope in classical cryptography. And throughout ages, this idea has been implemented in a variety of ways, like this about 200 years ago, this about 50 years ago. This was the Enigma machine that the Germans used during the Second World War, not knowing it had been broken before the war even started. This is DES, which is being phased out, but it's been used for quite a while. Well, the point is that throughout ages, really 4,000 years, as I said, people have thought of ways of using this basic paradigm to communicate confidentially. And again, throughout history, it's always been broken, at least until fairly recently. So far, code breakers have had the upper hand over code makers. Now, what we want, of course, the Holy Grail, if you wish, is unconditional security. Unconditional security means that no matter what the eavesdropper can do, no matter what his computing power or his technological sophistication, there's nothing he can do to decipher, to decrypt these messages without knowing the key. And none of these systems I showed you, including DES, is unconditionally secure. In fact, just about all cryptography that's been invented can be broken easily, quote easily, with unlimited computing power. And most of it can be broken easily even without it. But still, in the 1910s, a system was invented which is unconditionally secure, known as a one-time pad. It has problems with it, but let me spend a few minutes to tell you about a one-time pad because it's cute. Here's the idea. So this is a purely classical system, provably unbreakable, proven secure, unconditionally secure by Shannon in the 1940s. This is the key. Let's say Alice and Bob share this secret key. And the eavesdropper does not have it. Now, if Alice wants to send some message to Bob, She takes the clear text, she takes the key, puts them together somehow, and produces a ciphertext. Now Bob, who has the key as well, will receive the secret message sent over from Alice to Bob over an insecure channel. And then if an eavesdropper intercepts this ciphertext, it's a theorem of Shannon. There's no information at all about the clear text, except for its length. Now Bob gets the ciphertext, and all he has to do is put it together with the clear text, and out comes, put the key and the ciphertext together, and with a little luck, you can see the clear text coming out. I'm not doing too well today, but if I were just slightly more depth, well, what you would see, is this, because Vernam is the inventor of this crypto system. And now let's imagine that Bob is very happy about having deciphered this message, and he decides to answer Alice, so he takes the same key again. And by the way, now, just so that you won't call me a cheater later, the first ciphertext I put here. Now, Bob is going to answer Alice by using the same key and making his ciphertext that he will send Alice. Of course, he doesn't send the key, but Alice has the key. Now, Alice has the key, not the eavesdropper. The second ciphertext comes along. Alice takes it with the key. Oh, that works better. And gets to see Alice's, Alice gets to see Bob's clear text, Gilbert, which is Vernam's first name. And they're very happy, and they keep talking. And they're being fooled. They're fooled because this system is called a one-time pad. And it's called a one-time pad because it should be used only one time. And they've used the same key twice now. And that's enough to make the system insecure. This was Bob's message to Alice, ciphertext. See, it's here, didn't cheat. This was Alice's ciphertext to Bob. The eavesdropper got to see both of them. And even though Shannon proved that either one of them gave no information about the corresponding clear text, if you have both at the same time, which the eavesdropper does, you don't need the key. You just put them together, and you see both clear texts. There. Right? So the one-time pad, again, if I were slightly better at lining things up, you would see that. In other words, the one-time pad is provably secure, yes, if you use it correctly, namely once only. And what that means is that for the one-time pad to be used, you need a whole lot of key. And now the question is, how can Alice and Bob exchange secret keys and be sure that indeed the key is shared and secret? And in fact, if we come back to the paradigm of cryptography, really there are two problems to be solved before this can be put in practice. One is, if indeed Alice and Bob share the secret key, how did they use it to encipher and decipher messages? And one possible answer is one-time pad. It's the best answer if you want unconditional security. If you're happy with less security, then there could be other systems that require less key, smaller keys. But that's only one of the two questions. The other issue is, how do they get this secret key in the first place? And you must address both issues if you want to do cryptography. Now, quantum cryptography will use the one-time pad. So quantum cryptography will encipher and decipher with this one-time pad classical system, and will only address the issue of how to share the key. But whereas classical ways of sharing a key are always breakable, at least in principle, historically these keys for one-time pad, one-time pad has been used in real life for very important transmissions, like the red telephone between Washington and Moscow was using that. But historically, the way this key was shared between Alice and Bob was probably through a diplomatic briefcase. And, well, that's pretty good, of course, but it's certainly not unconditionally secure. Nowadays, keys are exchanged using public key cryptography like the RSA crypto system. That's also very nice, and that's definitely not unconditionally secure. If you have unlimited computing power, all these public key systems are broken by definition. So if we want unconditional security, again, we need to use a one-time pad, and we need to have a way to exchange secret keys in a way that's unconditionally secure. And that's where quantum mechanics enters the game. And the essential idea, it's all summarized in this transparency, and everything else is filling in the details. If I use two non-orthogonal polarizations to encode bits 0 and 1, then because quantum information cannot be measured reliably, it's impossible, even in principle, this is impossible unless quantum mechanics falls flat, which could happen. The impossibility of distinguishing between these two quantum states is in principle. Doesn't matter what technology you have at your disposal, you will never be able to distinguish between these two states, at least not with certainty all the time. It's a theorem of quantum mechanics, as long as the axioms hold. So these two states cannot be distinguished reliably. And let me be more precise what I mean. No apparatus can distinguish between these two states both all the time and with perfect reliability, or even close to perfect reliability. It is possible to distinguish between these two states sometimes with perfect reliability, or all the time with imperfect reliability. But all the time with perfect reliability is impossible, and that's what will make eavesdropping impossible, as we'll see in a moment. So because of these properties of quantum information, any eavesdropping attempt on a channel that carries only these two states will yield incomplete information and create errors, will disturb the state, and which will create errors, and these errors will be detected by Bob. So Alice is going to feed the channel with these states. I'll give the details in a minute. This is just a high-level idea. Alice will fill in the channel, the quantum channel, with these states, and any attempt by an eavesdropper to figure out what's going on will create errors, and Bob will be able to detect these errors. And therefore, what quantum mechanics gives us for free as a gift is a channel on which eavesdropping can always be detected. So that we have a natural eavesdrop detection channel. Now, in cryptography, detecting eavesdropping is not good enough. If you detect that you've been eavesdropped on, that's better than not knowing, but it's too late. So in fact, we use the quantum channel not to send the actual sensitive information. We use the quantum channel to send a random string. If this random string is eavesdropped on, we detect it and don't use it. If it's not eavesdropped on, then we share a secret random string, which we can use as a one-time pad, to classically encode the actual sensitive information. In other words, the actual message you want to transmit will not enter the game, will not be input to anything, will remain in Alice's laboratory until Alice and Bob have succeeded at exchanging a secret key. And that's why it remains uncompromised. The best the eavesdropper can do by continuous eavesdropping will be to make them fail at establishing a secret key, and therefore fail to communicate. But eavesdropper will not be able to make them believe that they are safe to communicate this sensitive information when they are not. Here's another picture of the same idea. So the one-time pad, in other words, a one-time pad allows to transform what is naturally an eavesdrop detecting channel into an eavesdrop prevention channel. Okay. Again, another picture of the same idea. Alice puts in quantum states into the channel. If an eavesdropper tries to measure it, that would create disturbance, and what gets to Bob is different from what Alice had sent. So at this point, the good news is that quantum information, and the good news is that there's no way for the eavesdropper to learn the information that Alice is trying to send Bob. And the bad news, if you're at all awake, is that there's no way for Bob to read it either. So we need to figure out a way for Bob to get the information. Okay. Now let me just tell you a little bit more about photon polarization before we go on. There are such things as polarizing filters. You've all seen those things, perhaps in 3D movies or in camera material. For instance, this filter polarizes light horizontally, and this one vertically. Now, if you have a horizontally polarized photon that hits this filter, it goes through. If it had been vertically polarized, hitting the same filter, it would be blocked. Again, nothing, I hope, that's surprising. We can see here, this again is a horizontally polarizing filter. It doesn't have any effect on these photons polarized horizontally, and it blocks all of those polarized vertically. Okay. So it is possible, in fact, to distinguish. I said before that it's impossible, even in principle, to measure quantum information. In some cases, it is. If you know ahead of time that a given photon is polarized either horizontally or vertically, then you can tell the difference with arbitrary accuracy. It's only if you have no prior information that you can't. Or similarly, you could distinguish with arbitrary accuracy between a photon polarized at plus or minus 45 degrees. Any two orthogonal polarizations can be distinguished reliably. Now, what happens if you have a photon coming in, say, at 45 degrees, like this one? Well, again, if we have a filter that transmits horizontally polarized photons, then there is a probability 1/2, if in the case of 45 degrees, probability 1/2 that the photon goes through, in which case it will be polarized horizontally. And probably 1/2 that it is blocked. And I'm lying to you. I'll come back to that. So in this case, for instance, if I have this horizontal filter, and all the photons coming out here are polarized at 45 degrees, then half of them will go through, and half of them will be blocked, so we lose half the photons. And this, according to quantum mechanics, is a purely random process. There is no predetermination as to which will go through, which will be blocked. And Einstein hated that. Okay. Now, when I said I lied to you, really, it's because what really happens, but we don't need to know that for quantum cryptography. It is not for the simplest schemes of quantum cryptography. What really happens that each photon hitting the crystal, or sorry, the filter, will simultaneously go through and be blocked in quantum superposition. It's only when it is detected that a decision is really made. Although in this case, being blocked is akin to being detected, so perhaps some people would disagree with what I said. So instead, let's take a more interesting device to see this at work. This is another kind of device to measure polarization. It's a little crystal, a crystal like this, a calcite crystal. It's getting cloudy with age, but essentially what this crystal does is that it has two axes of propagation for light inside the crystal. One axis that propagates horizontal polarization, one that propagates vertical polarization. So that if you input a vertically polarized photon, it will go up, horizontal will go down. And if you take a diagonal photon, well, half of them will go up, half of them will go down. But they are repolarized according to which path they decided to follow. And this is where I'm lying to you. In fact, each photon will go on both paths in quantum superposition. And it's only if detected that you can tell that the decision is made. But that's irrelevant for this talk. So it's OK if you think of the photon as making a random decision when it hits the crystal, rather than when it is detected. All right. For instance, here I have this little black dot, which is now split by the crystal between a horizontally and a vertically polarized black dot. And you can see that I'm not lying, because if I put this vertical filter, one of them appears, only one of them disappears. If I turn it slowly, you will see that the other one will appear instead. Right? So these two dots are polarized. And you can tell with this filter. Good. Enough with that. Let's go back to cryptography. Oh, no. I still need to show you a magic trick. So you have at least one thing to go home with if everything else bores you. Here I have two filters, cross filters, and therefore they block the pathway of light. Nobody is surprised. Now, in classical mechanics, if you have a device that blocks the pathway of light, like this one, for instance, then it's not by adding something else, one more obstacle to the pathway of light, that you will make it reappear. Unless what you put in, of course, is the light itself. This is not a light. And however, with quantum mechanics, strange things happen. I add one more obstacle to the pathway of light, and light reappears. There. Okay. Back to cryptography. Or maybe just, again, in fact, I said before that if you want to distinguish between horizontal and vertically polarized photons, then you could use just a filter and a detector. In principle, that's perfect. In practice, that's not very good because detectors are not perfect. Sometimes detectors will not see an incoming photon, in which case, if you don't see it here, you don't know if it's because it was vertical and blocked or horizontal and not detected. And that's why this is a better device to distinguish between the two polarizations. If you see it here, it was vertical. If you see it here, it was horizontal. If you don't see it, you lost it. But it's better to know that you lost it than to think that it was something it's not. So we're going to, in practice, because this is talk about, contrary to most things you will hear this week, this is real. This has been built for real. So in real life, this is the way that you distinguish between single photon polarization, which we need to do to implement quantum cryptography. Good. Now I'm ready to tell you how to do it really. Before I just said that Alice sends these photons to Bob, and the eavesdropper will not be able to measure them, but Bob will not be able either, so what's going on? Yeah, this is what's going on. We're going to use there are many ways of doing it. This is the simplest way. It's not the best, but it's the simplest way. We're going to use the following coding scheme. Don't really read that. The point is here. The coding scheme is as follows. Whenever Alice... let me try again. Alice is going to prepare two long random strings. Sorry. Alice is going to prepare one long random string. And for each bit on her string, she will prepare and send one photon to Bob. In the ideal scheme, she will create one single photon of chosen polarization and ship it over to Bob. In practice, we have to do something which is not quite as good, but that's okay. And by the way, when I said before that you cannot measure photon polarization with arbitrary accuracy, this is true. But on the other hand, it is possible to prepare a photon with arbitrary accuracy. So if you want to prepare a photon with 23.56 degrees, you can do that. In principle, there is no limit at how precisely you can prepare a photon. It's measuring them you cannot do. So Alice, at least in principle, can prepare photons of these two types without problem, as she wishes, and send them to Bob. Now the protocol goes as follows. For each 0 in Alice's string, she will send a vertically polarized photon. And for each 1, she will send a 45-degree photon. And then, when Bob gets these photons, they'll have to be synchronized somehow. When Bob gets a photon, I didn't say, but Bob also has a random string. Both Alice and Bob chose independent random strings. What Alice does with her random string is what I just said. What Bob does with his random string is to decide on measurements. He will either measure the photons according to horizontal versus vertical polarization, and he will do that if he has a 1 in his random string. But if he has a 0 instead, then he will measure the photons one diagonal versus the other. And in particular, Bob will ask the photon are you horizontal, or are you minus 45 degrees? And now let's see what happens on an example. I'll put the scheme here. Let's see what happens on an example. Let's say that Alice's bit string is this, and there's Bob's bit string. Then in the first time slot, Alice has a 1. Therefore, she will prepare a 45-degree photon. Alice will prepare a photon polarized at 45 degrees and send it to Bob. Now, Bob has a 0, and therefore, Bob will ask his photon, are you, let's see. Did I get it wrong? So Alice has a 0, sorry, yes, right. Alice has a 0, and therefore Alice will ask Bob will ask his photon, are you polarized at minus 45 degrees? So if we forget about crystals and that, if we do it the easy way, Bob will put in a minus 45 degree filter, and of course will not see the photon. So Bob will say, I did not see it. Okay. Go to the second time slot. Alice has a 0. A 0 means Alice will prepare a vertically polarized photon, like so. Bob has a 0 as well. And therefore, as before, Bob will measure at minus 45 degrees. And this time, there's a half chance Bob will see it. And if Bob sees it, Bob will tell Alice, OK, we keep this one. If he doesn't see it, he will say, we don't keep it. Now, the point is that it's only, except for experimental error and except for possible eavesdropping, it's only possible for Bob to see Alice's photon when the two filters are not crossed, which means either if Alice had a 0 and Bob measured 0, or if Alice had a 1 and Bob measured 1. Because in the other two cases, if Alice had a 0 and Bob measured 1, they're crossed, therefore the photon will not go through. Or if Alice had 1, as we saw before, and Bob had a 0, they are crossed, and the photon will not go through. So when Alice and Bob's bits are different, the polarizer are crossed, and therefore Bob will always say, we don't keep this bit. When they have the same bit, they're not crossed, and there's a half chance that Bob will say, we keep it. So the bottom line is that Alice and Bob initially chose two very long independent random strings. And what this process will do, it will delete all positions in which they did not choose the same bit by chance. And it will unfortunately also delete half the position where they had the same bit. So in the end, they will have a string which is 1/4 the original length, but which is perfectly shared. And it's also perfectly secret if there's no eavesdropper, of course. But if there is an eavesdropper, there are two types of eavesdropper. If the eavesdropper only listens to the classical communication in which Alice and Bob said what they keep, what they don't keep, then it only says keep, don't keep, don't keep, doesn't say anything about which bit it is. So the only way the eavesdropper can hope to learn something about the actual key is by eavesdropping on the quantum transmission, by trying to do something about measuring these photons of Alice. But again, any attempt at doing that will disturb them in a way that will create errors. And whenever Bob thinks that he's gotten the right bit, sometimes he will have the wrong bit. And that's why it becomes complicated. And I will not get into detail. But at the end of this process of quantum key exchange, Alice and Bob will compare some fraction of their bits. And if the error rate is very low, they will blame it on natural errors. If the error rate is too high, then they will say it's because there was an eavesdropper over there. And now we need to have a very complicated formula, which has been worked out by Dominique Myers here, that tells you as a function of the error rate, what is the maximum amount of information that an eavesdropper could have gained creating this much error. And once we have an estimate on the amount of information the eavesdropper has gained, if it's low enough, it can be eradicated. You can remove this information that the eavesdropper has gained by classical protocols called privacy amplification, which I will not have time to describe. Whereas if the information gained by the eavesdropper is too high, then Alice and Bob just give up. They do it again, perhaps. But in any case, they will not use a key that has been compromised to send sensitive information. Because remember, until now, the actual message has not entered the game. So either there's a little or no eavesdropping, in which case Alice and Bob will succeed at distilling maybe a shorter key but perfectly secret that they will use as a one-time pad to send a message. Or there is too much eavesdropping, in which case Alice and Bob will know and will just have to give up. But in any case, the actual sensitive information remains secret. So in other words, the best that the eavesdropper can do is jam the channel, which in practice you can also do by dropping a bomb on Alice or Bob. Okay, so this is the basic idea of quantum cryptography. What I described to you is known as the B92 protocol, invented by Bennett in '92. The original BB84 protocol used 4 states instead of 2. It's slightly more complicated, but it's basically the same idea. Yes, question?
When you said they'll compare, you mean not using
Classically, they will classically compare. Alice will randomly choose for each position whether to disclose it to Bob or not. And if it is disclosed, then it's, of course, not used anymore as a secret bit. Instead, it's used as a test. So this, the only quantum part is this. Once this quantum key distribution is finished, everything else is purely classical. That is, the assessment of error rate is classical. Error correction, because if there are errors, even if you decide the error rate is low enough that there has been no eavesdropping, still you have to correct the errors. So the error correction is classical. If you decide that the eavesdropper has some information, you have to remove it by privacy amplification. That's also classical. So after this, everything is classical. Okay. So again, this is the basic protocol. Arthur Eckert, in 1991, proposed a protocol that uses entanglement and Bell's inequality. It was a very beautiful protocol, which is less practical, perhaps, but which had the merit of making physicists aware of this whole topic, because he used Bell's theorem. And so therefore he could publish in physical review letters and all that. So really, I'm slightly facetious, but the truth is that Eckert's paper was instrumental, by being in physical review letters, in bringing physicists into the picture, and thus making the whole field much more fruitful. Okay, so much for the theory. In practice, how do you do that? If you want to implement quantum cryptography, the way I explained it, what I explained is really an ideal protocol. In practice, you cannot make single photons as if they were ping pong balls and polarize them one by one and shoot them over from Alice to Bob and be sure that Bob gets it and measures it with certainty and that everything is perfect. In practice, there will be errors. In practice, sometimes Alice thinks she sends 1 photon to Bob, but there are 2. So there are all kinds of things in practice that you have to take account of, which makes it less clean. But still, with current technology, it's perfectly manageable. For example, in Scientific American of October 1992, Charlie Bennett and I, with Arthur Eckert, explained all the principles of quantum cryptography. It's probably the best place to look at it if you want to look at the early ideas. October 92 Scientific American is the easiest reading. And there we described our original prototype that Charlie and I built with students, in which, for the first time, we realized provably secure key exchange over a distance of 32 centimeters. Here's Alice, and there's Bob. And again, this is a provably secure key exchange. Of course, there was a big box on top of that, and we checked that there was no eavesdropper in there. And this was provably secure as long as the eavesdropper was deaf, because you see the biggest piece is the power supply, which is used to rotate photons under the computer's control. And this thing works, the thing that rotates the polarization is known as a Pokel cell. It's somewhere around here. And you need to apply about 1,000 volts on a crystal to make it move a little and turn polarization. And the power supplies the biggest piece here to apply this 1,000 volts made a lot of noise, and you could literally hear the bits go through, and well, zeros and ones did not make the same noise. But that's okay. Well, point, of course, Charlie and I by no way, we're not experimentalists. We just had fun doing that. But then real people, I mean, experimental physicists starting having fun as well. At Los Alamos, there was a prototype working on over 48 kilometers of distance compared to 32 centimeters. This is the lab's layout. Alice was here, put in little photons in the fiber here, and went all the way here. In fact, this is only 12 kilometers. There was a mirror. It bounced and came back, and bounced again and came back, and bounced again and came back for a total of 48 kilometers. But of course, Bob was right next to Alice. See, here's Alice, and there's Bob, with the fiber going up at the ceiling and coming back. But still, we can believe they didn't cheat. And the point is that the photons really travel in real conditions, not as pool in a laboratory. Right? They went underground, and it worked except on Wednesday nights, because on Wednesday night, the janitors played poker in the basement, and they banged their feet so hard, and really, I'm not kidding you, just by banging their feet on the floor, they disturbed the photons, and it didn't work on Wednesday nights. But still, I prefer the experiment in Geneva, in which Alice was in Nyon, and Bob somewhere in Geneva here, and there was a fiber under the lake. This is the Lake of Geneva. There was a fiber, the 23-kilometer length of fiber, and by this time Alice and Bob are really separated. And in fact, this they've improved it to in fact 67 kilometers now between Geneva and Lausanne. And what they have is a plug-and-play system in which they have a little device called Alice that they plug at one end of the fiber, a little device called Bob they plug at the other end of the fiber. So here's Alice, there's Bob. And they look the same, but they're very different inside. And you just have an arbitrary 67 kilometers of fiber between them, and it works. Just push buttons, it works by itself. It's really remarkable. It's remarkable because optical fiber messes up polarization, so you have to do something around that. But I won't get into the technical details. However, if you want one, it's available for sale. No, they really set up a company to sell that thing. It's called ID Quantique in Geneva. ID Quantique, can't see it really. So ID Quantique markets this device. They haven't sold one yet, they told me. But they also market single photon detectors at telecom. You see, the fiber here is a real telecom fiber. It's not a special purpose fiber. It's at the usual telecom frequency on which it's hard to have good single photon detection. So they've also designed a now commercially available photon detector which they sell 30,000 francs and Swiss francs, and that does the job for detecting photons at that frequency. And that they have a backlog of orders for that. Anyways, let's go back to more serious for science. Other prototypes exist which do not use fiber. Instead of inputting the photon in the fiber and having it travel some distance over the fiber to Bob, it's also possible to have a line of sight setting, in which Alice sits on one mountain, Bob is on some other mountain about 20 kilometers further, and he sends single photons through air in broad daylight, and Bob can tell Alice's photons apart from all the photons coming out from the sun. This has been done as well, over tens of kilometers between two mountains. Now, I forgot who's done that, I'm sorry. Richard Hughes was the first one to do that in Los Alamos, over 1.5 kilometer. One footer. Okay, so it's what's that? Okay, so Rarity and 1 footer. And what's the distance exactly they've done? 20 something?
I think it's 13 kilometers.
30?
13.
13. Well, more than 10. The pioneer for that was Richard Hughes in Los Alamos, who did that in the canyon, over 1.5 kilometers. That's pretty good already. And they've done it in 1 footer and Rarity over 2 mountains in Europe. Okay. I have only about 5 minutes left, and I'm about 1/3 through my talk, so I have to go slightly faster. Let me just mention that there are limits to quantum cryptography as I've described it. I have a paper with Tal Moore, Barry Sanders, and Norbert Lukenhaus that explains why, if you're not careful, right? What Dominique proved is that if you implement quantum cryptography according to the ideal protocol I described, or maybe BB84 I didn't describe, it is provably unconditionally secure, period. But when it's implemented, people don't do it exactly right, and if you're sufficiently uncareful, well, then it can be insecure again. So you really have to be careful how far from the ideal protocol is your implementation before it's really secure. And this paper analyzes some loopholes if you're really easy to implement eavesdropping attacks if you're not careful enough in your design. And I would say that most, if not all, prototypes currently existing fall under the loopholes. So as far as I know, we don't really have a prototype that is really secure, but the technology to do it is here. And perhaps I'm wrong. Perhaps some of these prototypes are careful enough, but most aren't. Okay. Now let me go to the second half of my talk, which is about going beyond key distribution. What I've described so far is how to use quantum mechanics for the primary goal of cryptography, which is to allow two people to communicate confidentially. But cryptography doesn't stop there. There's a whole bunch of things you can do with cryptography, and especially has been developed in the past 25 years since Diffie and Hellman came along, other than just secure communication. And none of these things can be done classically with unconditional security, except for some forms of authentication. But the thing that you hear about in modern cryptology, like public key cryptography, like signature, bit commitment, coin flipping, zero knowledge, all of these things, in fact, can be broken with sufficient computing power. Again, zero knowledge is sometimes not true what I said, but most of these things will fall against a classical attack which has enough computing power. And those that don't, we don't know how to prove that they don't. So it's a natural question. If quantum mechanics allows to send confidential information in a way that's provably impossible, I forgot to mention that, but what quantum key distribution achieves was proven by Shannon to be impossible, of course, in the classical world. So if quantum mechanics allows you to do something that's provably impossible, why not something else? So it's a very natural question to look at all of these other things that modern cryptology offers, which are protected at best computationally, and see how many of those could be done with unconditional security using quantum mechanics. For example, and in fact, to be historically exact, in fact, the very, very first idea that the precursor of quantum cryptography, Stephen Wiesner, I talked to you about in 1970. Right, I show you his quantum banknote. Well, in the same unreadable paper, he also proposed, unreadable for computer scientists, of course, he also proposed quantum multiplexing. So in the same paper, Stephen Wiesner gave quantum banknotes, and he proposed a quantum channel, on which Alice could send two messages to Bob in a way that Bob could choose which one to read, but whichever he would read would destroy the other. So that Alice inputs two messages, and Bob chooses to read one or the other, and gets to read whichever is chosen, but cannot get to read both. And of course, Alice doesn't know which one was chosen by Bob. Now, if you're a computer scientist, you've heard of that as oblivious transfer. Now, oblivious transfer was not invented by Rabin in 1980-something. It was invented by Stephen Wiesner 10 years earlier. And he proposed a quantum implementation. However, Wiesner's implementation was flawed, and he knew it. His paper explains how to break it. So the original Wiesner paper explains quantum banknotes, quantum multiplexing, and how to break it. But still, in the beyond key distribution scenario, in fact, multiplexing is beyond, in the sense of being something different, but it predates key distribution. Now, I'm really running out of time. I'll take a few more minutes to tell you quickly about these things, coin flipping, bit commitment. Well, coin flipping is a process by which Alice and Bob want to flip a coin, and they don't trust each other, but they want to have a fair coin flip. How can you do that? This notion of flipping coins over the telephone was invented by Manuel Blum in the early 80s, and it was one of the really most beautiful ideas in early ideas of modern cryptology. That's coin flipping. But it's not possible. This cannot be done classically again. And classically, any coin flipping protocol you would invent would be completely breakable by at least one of the two parties with enough computing power. Can you have a better quantum coin flipping protocol? And I will tell you in a minute. Second example, bit commitment. Here's the idea. This is a classical analog of what we want to achieve. We want to achieve a scheme by which Alice can take either a bit or a bit string, put it in the safe, close the safe, and send the safe over to Bob in such a way that at this point, after committing phase, Bob does not know what's in the safe because he doesn't know how to open it, but Alice cannot change it anymore because the safe is in Bob's hands. But later on, Alice, if Alice wants to open the safe, she just tells Bob how to open it. Bob opens it and gets the output. So such a bit commitment is known to be binding if there is no way for Alice to change what's inside, and hiding if there is no way for Bob to know what's inside until it's unveiled. Again, it's not possible to do classically except computationally. Oblivious transfer is the modern name for multiplexing channel, in which Alice has maybe inputs 2 bits to some box, and Bob inputs which of the 2 bits he wants and gets to know the chosen bit, but does not get to know the other bit, and Alice does not get to know which bit is chosen by Bob. And my last example here corresponds to discrete decision making, is as follows. Again, classically, there could be several parties here. They each have some input to a function f, and they wish to compute. They all wish to learn what's f of all of the joint inputs, but they don't trust each other with their inputs. So Alice doesn't want anybody else to know what x is. Bob wants to keep y private, but they do want to collaborate so that they will all learn f of x, y, z. Again, it's a basic cryptographic goal that you may want to have. And make a long story short, bit commitment is a very powerful primitive, because if you have bit commitment, you can do coin flipping and all kinds of other stuff like zero knowledge, identification, and so on. So bit commitment is a useful primitive to do many other things, but not everything else, because there are good reasons to believe that from bit commitment alone, you cannot do oblivious transfer. Whereas from oblivious transfer, you can do everything else. I don't have a slide for this, but from oblivious transfer, you can do discrete decision making. In other words, the 2 primitives are bit commitment and oblivious transfer. And of the 2, bit commitment is good enough to do all kinds of things, but not everything, because oblivious transfer is stronger, and oblivious transfer does allow for everything else. That's in the classical world. Now, in the quantum world, bit commitment gives oblivious transfer. So here's another example where using quantum mechanics, you can do things in cryptography which are not possible classically. Key distribution was the first such instance, but to build oblivious transfer upon bit commitment is only possible in the classical world. Sorry, in the quantum world. Okay, I'll take just a few more minutes to tell you, therefore, and therefore, bit commitment is the holy grail for cryptography in the quantum setting, because once you have bit commitment, essentially you can do everything else you might. Just about everything that has cryptographic significance can be obtained, provably secure, from a primitive that gives you bit commitment. So what about bit commitment? In 1984, Charlie, Bennett, and I had a bit commitment protocol. Just following the steps of Wiesner in the same paper, we showed how to do it and how to break it. And it took almost another 10 years before Claude Crépeau found a way to do it. So in 1993, there was this paper at Fox in which we showed how to do bit commitment in a way that's unbreakable, proved unbreakable, and therefore quantum cryptography could do everything any cryptographer ever dreamt of. And it was the end of the story. And there would be nothing else to think about in quantum crypto unless something happened, which it did, because Dominic Myers was very nice to prove the security of key distribution, but he also proved that bit commitment did not work. In other words, this Fox 93 paper was wrong. Our construction was wrong. There was a flaw, a subtle flaw that Dominic found, and independently found by Liu and Xiao somewhat afterwards. And then Dominic and I and Claude tried to find a way to patch this construction because we really wanted to have bit commitment, and Dominic proved it's impossible. So that's bad. All right. I'm really over time, but let me try to finish on this. That bit commitment, if we had perfect bit commitment, in the quantum world, you could do this as in the classical world, but a lot more. But you cannot have it. It's not the end of the story. There are two directions still alive. One is to get bit commitment, which is, since you cannot get it unconditionally secure, how about getting it computationally secure? And Claude Crépeau is working on that with students and Paul Dumais, for instance, on reviving a computationally secure bit commitment only based on one-way permutations. And once you have that, then again you can build oblivious transfer. So it's possible to have oblivious transfer based only on one-way permutations quantumly, whereas classically you cannot do that. And the other direction is that bit commitment allows to do that. Bit commitment is dead, at least unconditionally secure. Doesn't mean that those are dead. And indeed, quantum coin flipping can be done. There is a quantum coin flipping protocol which is provably better than anything you can do classically. And I'm not going to show you the protocol, I'm just going to tell you what it does. This was found by Anderson Bynus, who will give one of these talks here. Coin flipping is easy to do if you have bit commitment, but now we want to do it some other way. And what Andres found is a coin flipping protocol by which both Alice and Bob could cheat, but not completely. And that if only one of them cheats, if they both cheat, we don't care. If only one of them cheats, the best he or she can do is to get a coin flip come out the way he or she wants with probability 3/4. Whereas again, classically, no matter how you try to do it classically, one of the two parties can always get a coin flip to come out the way he or she wants all the time, with enough computing power. Quantumly, there's a coin flip protocol that neither party can bias by more than 75%. So again, another example of something you can do with quantum mechanics in cryptography that is provably impossible classically. And there are other examples. I'll say something about the Byzantine agreement that Nicolas Gisin has and Willy Maurer have found. And it goes on and on. So now I guess I don't have an open question slide here, but the best open question is, what else? Try to find all the things that quantum mechanics give you in cryptography, even if it's not perfect, but that they give you provably better than you can do classically. And we have some examples, but surely there is more to be found. And I guess I better stop here. Thank you. There's minus 10 minutes for questions. Okay. Thank you.